Hello everyone. We are now going to begin our study of the graphs of other trigonometric functions. In the previous lecture, we learned about the graphs of the sine and the cosine functions. We left out the tangent, the cosecant, secant, and the cotangent function graphs. And there was a reason for that. The sine and the cosine function graphs are continuous graphs, whereas the rest of the trigonometric functions have graphs which are not continuous. They have points where the functions are undefined. So those graphs have a different set of properties that we will need to learn about in this lecture. These are the topics that will be covered in this lecture. We are first going to look at the tangent function graphs, understand the behavior and the properties of the tangent function graph, look at the variations that we can get in the tangent function graphs. After that, we will go on to the cotangent function graphs, which is the reciprocal of the tangent function, look at its variations, and finally learn about the cosecant and the secant function graphs as well as their variations. Let's study the shape and the behavior of the graph of the tangent function y equals tan over x. We have here listed in this table different x values between 0 and pi over 2, and below we have the corresponding y values for each of the x values above, given in radians. So the range here of the x values extend from 0 to pi over 2. Let's observe the progress of the y values as we move from 0 to pi over 2 for the x values. When x is 0, tan of x is 0. When x is pi over 6, it's square root over 3 by 3. In decimals, that's approximately 0.6. At x equals pi over 4, we have a y value of 1. At x equals pi over 3, we have 1.7, which is the decimal of square root over 3. At 5 pi over 12, it's 3.7. 17 pi over 36, it's 11.4. 89 pi over 180, it's 57.3. At x equals 1.57 radians, it's 1255.8. And then finally at pi over 2, the value of y becomes undefined because we end up dividing the ratio by 0. So undefined is the same as infinity, a very large value, correct? So what we observe here is that the y values start from 0 and they keep increasing gradually at first, and then suddenly it shoots up from 11.4 onwards to 57.3 to 1255.8, and then finally at pi over 2 it reaches infinity. It is undefined. So the picture here of the graph shows the shape of the graph. At the point of origin, we have the y value at 0, and then we see the graph grows, the values increase. So the graph rises slowly, and then it's a sharp rise, almost going vertically up. And at the asymptote here, this dashed line at pi over 2, and there's another asymptote at negative pi over 2, the graph reaches infinity. So with the asymptote, it tells us that the graph will go up, increase rapidly to infinity. It will not cross pi over 2. So on the negative side, when the x values are negative, the same happens, only that the y values are all negative. Recall that tangent is an odd function. When we replace the x values by its negative corresponding values, then the y values will also become negative. Okay, so let's go over some of the properties that we can derive from this behavior of the graph. First of all, the period of the tangent function graph is pi. That means one cycle of the graph will complete within pi intervals. In this case, in this picture, it starts from negative pi over 2, and then on the right hand side we have pi over 2 where the asymptotes are located, and this interval is pi units. Minus pi over 2 to positive pi over 2 is pi units. The next property is that the tangent function is an odd function. We've already observed that when we replace the x values by its corresponding negative values, then the y values tan of x becomes negative. So that's what we see here. The graph moves along the negative y axis. And then finally, the tangent function is undefined at x equals pi over 2. On the negative side, it's negative pi over 2 as well. So that also tells us that the graph has a unique cycle between pi intervals, and then the graph keeps repeating as we extend the x-axis and draw the graph on different cycles. All right? Here's a summary of the characteristics of the tangent function as well as a picture of the tangent graph over different cycles. The first characteristic is that the period of the tangent function is pi units. The domain is all real numbers except odd multiples of pi over 2. The domain represents all possible x values that can be input into the tangent function. We can input any real number for x except odd multiples of pi over 2, which means pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, all the odd multiples, and the same is true on the negative side as well. So negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, they will all have asymptotes at those points. The range would be all real numbers. So again, this is a picture of the tangent function over different cycles. There are some more characteristics of the tangent function that we will study next. In the next set of characteristics, we look at the vertical asymptotes. They are located at odd multiples of pi over 2. We discussed that previously. The asymptotes will be located at pi over 2, 3 pi over 2, 5 pi over 2, and so on as we move to the right. On the negative side, again, it will be at negative pi over 2, negative 3 pi over 2, therefore odd multiples of pi over 2. And those are the points where the graph will reach infinity. About the x-intercepts, an x-intercept occurs midway between each pair of consecutive asymptotes. So between negative pi over 2 and pi over 2, the x-intercept, where y is equal to 0, is right midway between these two asymptotes. Same here between pi over 2 and 3 pi over 2. The x-intercept, where the y value is a 0, occurs at pi because that is the x value right at the center between pi over 2 and 3 pi over 2. And that is true for every cycle. Therefore, x-intercept occurs midway between the halfway point between each of these asymptotes. The graph is an odd function with origin symmetry, and finally points on the graph 1/4 and 3/4 of the way between consecutive asymptotes have y coordinates of -1 and 1 respectively. What this means is that 1/4 into the cycle, into each cycle, the graph will have a y value of -1. So if we move from negative pi over 2 to positive pi over 2, 1/4 way is right here that has a y value of -1. So at negative pi over 4, we have a y value of -1, and then 3/4 down, we see the x value would be pi over 4, and that would have a y value of positive 1. So what it says here again is points on the graph 1/4 and 3/4 of the way between consecutive asymptotes. So that means along the cycle we'll have y coordinates of -1 and 1 respectively. Let's look at graphing the variations of the tangent function graph. The equation of the tangent function graph variation is given to us as y equals a times tan of, within brackets, bx minus c, where b is greater than 0. Now the steps to graph the variations of the tangent function would be a little bit different from the sine graph or the cosine graph, because here we have asymptotes to consider. So we begin graphing by first locating the points where the asymptotes would be located. So the first step here says find two consecutive asymptotes by finding an interval containing one period. The period of the tangent function is pi units, so the asymptotes would be located at minus pi over 2 less than bx minus c less than pi over 2, and the location of the asymptotes would be an x value which we will obtain by solving the equation bx minus c equals negative pi over 2 and bx minus c equals pi over 2. So that's where the pair of consecutive asymptotes would be located. So the first step involves solving for x in these two equations. The second step is to identify an x-intercept which will be located midway between the two asymptotes we found in step 1. In the third step, we find the points on the graphs 1/4 and 3/4 of the way between each cycle. That means between the consecutive asymptotes. And recall that in the basic function, 1/4 way into the cycle, we had a -1 for y, and 3/4 way into the cycle, we had +1 for y. Here, those values would be determined by whatever value a has. So 1/4 way, it would be -a, and 3/4 of the way into the cycle, it will be a +a. And finally, in step 4, we are going to use the steps 1, 2, 3 to graph one full period of the function, and if needed, we can add additional cycles to the left as well as to the right. Let's look at a pictorial view of the steps of graphing the tangent function. The first step was to find the location of the two asymptotes, which will also encompass one full cycle of the graph. The left-hand side asymptote would be determined from this equation bx minus c equals negative pi over 2. On the right-hand side, the asymptote would be determined from the equation bx minus c equals pi over 2. Remember that the asymptotes in the variations are not necessarily negative pi over 2 and positive pi over 2 as it is in the case of the basic tangent function. The asymptotes will be determined by solving for x in each of these two equations. Bx minus c equals negative pi over 2 and bx minus c equals positive pi over 2. So that's the first step. Let's write that. Step 1 of the graphing process. In the second step, we identify the x-intercept, which is midway between the two asymptotes. So this represents step 2 in our graphing process, and step 3 would be to determine the y coordinates 1/4 way into the cycle, which is here, this value. So this is step 3, as well as 3/4 way into the cycle. This is again step 3. And then finally we will draw the graph as part of step 4 using the right shape of the expected tangent function. Let's work on an example to graph a variation of the tangent function in the interval minus pi over 4 less than x less than 3 pi over 4. So the interval given to us between which the tangent function variation graph will need to be drawn is between negative pi over 4 and positive 3 pi over 4. The equation again given to us is y equals 3 times tan of 2x. We have to identify the values of a, b, and c in this equation. Again, the form is y equals a times tan of, within brackets, bx minus c. So if we use our equation that's been given to us, it's 3 for a, and then tan, and then within brackets we write 2x, 2 being the value of b, and we don't have anything after 2x, so it's minus 0. C has a value of 0, b has a value of 2, and a has a value of 3. Therefore, in the first step, we identify the values of a, b, and c. And just as we did, they got a equal to 3, b equal to 2, and c equal to 0. The first step is to identify the asymptotes using the equations, which would be bx minus c equal to negative pi over 2 and bx minus c equals positive pi over 2. We have to solve for x to find the location of the asymptotes. B has a value of 2, so let's replace b with 2. Same thing here, we replace, and c is 0, so let's get rid of it. So we'll end up with 2x equals negative pi over 2. When you solve for x, you will end up with negative pi over 4 would be one location where the left-hand side vertical asymptote would be located. 2x equals pi over 2. When you solve for x, you will end up with positive pi over 4 is the right-hand side vertical asymptote. I'm going to pull up here the first step. Find two consecutive asymptotes. Minus pi over 2 less than bx minus c less than pi over 2 is the inequality that we have to solve for x. So we have bx minus c is equal to 2x. When we solve for x in this inequality, we end up with minus pi over 4 being the left-hand side vertical asymptote and positive pi over 4 being the right-hand side vertical asymptote. That's the first step. So the interval containing one period is negative pi over 4 comma positive pi over 4. That's where the two consecutive asymptotes would occur. The next step is to identify x-intercept, which would be midway between the consecutive asymptotes, between negative pi over 4 and positive pi over 4. X equal to 0 is the midway between negative pi over 4 and positive pi over 4. Therefore, the graph will pass through 0, 0, where the x-intercept would be located. So let's look into the third step of our graphing process. In step 3, we will find the coordinates of points located 1/4 and 3/4 of the way from the left-hand side vertical asymptote. We also know that the y-coordinate of these points is going to be derived from the value of a in this function given to us. We are working with the function y equals 3 times tan of 2x. Here, the value of a is 3. However, 1/4 way down, the point is going to have a y value of negative 3. It's going to have a value y equals negative 3, and 3/4 way down, the y coordinate is going to be a positive 3. How do I know which one's going to be a negative value and which one's going to be a positive value? For that, we have to look at the shape and behavior of the tangent function. In step 1, we identified that the vertical asymptotes of this particular function would be located at negative pi over 4 and positive pi over 4. The midpoint of this function is going to be at 0, 0, and that is where the x-intercept of the graph is going to lie, correct? And the shape of the tangent function is such that as we go from the midpoint towards the right-hand side vertical asymptote, the y values rise. The graph rises above the x-axis. In other words, the y values are all positive values. It rises like this. Between the left-hand side vertical asymptote and the midpoint, the y values decrease. In other words, as we go from the midpoint towards the left-hand side vertical asymptote, the y values drop below the x-axis. The y values are all negative. Now, 1/4 distance between negative pi over 4 and pi over 4 would be somewhere right in between negative pi over 4 and 0, correct? And here the y value would be negative. So 1/4 way down from the left hand side, we will have a negative y value. 3/4 way down, which would be located somewhere here between the midpoint and the right hand side vertical asymptote, the y value would be a positive value. So that is how we know which point is going to have a negative y value and which point is going to have a positive y value. Now we need to find the x coordinates for each of these points. To find the x values, we substitute the y values into the equation given to us and we have to solve for x. And this is how we do it. We substitute -3. We first take the point which is 1/4 way down. We substitute the y value for it, which is -3, and we are going to solve for x here. So we need to isolate tan of 2x. In order to do that, we'll divide both sides by 3 to get rid of the 3, and we will end up with -1 equals tan of 2x. Now at this point, we have to go back a little to our special angles table and find out for what angle the tan ratio has a value of -1. Tan of negative pi over 4 equals -1, correct? Whenever the angle is negative pi over 4, the tangent function is going to end up with a -1 as its ratio. So this expression 2x can be equated to negative pi over 4. Therefore, we write it as 2x. This 2x is the equivalent of negative pi over 4. We write it in equation form without the tan, correct? We are just solving for x here. So 2 times x equals negative pi over 4. And now we can solve for x by dividing both sides by 2, and we end up with x equals negative pi over 8. To find the x coordinate of the point which is 3/4 way down, we substitute the y value with a positive 3. So we get 3 equals 3 times tan of 2x. Then we divide both the sides by positive 3 to come up with an equation which is 1 equals tan of 2x. Again, ask yourself, for what angle is the tan ratio a 1? For pi over 4. That means 2x better be equal to pi over 4 to get a ratio of 1. Therefore, we write the next step as 2x equals pi over 4 and solve for x and come up with an x coordinate value of pi over 8. So for 1/4 way down from the left hand side asymptote, the x and y coordinate would be negative pi over 8 comma -3, whereas 3/4 way down the coordinates would be positive pi over 8 comma positive 3. In step 4, We are finally ready to graph our function using the information we found in steps 1 to 3. Here is a picture of the graph. The original question had told us to draw the graph in the interval -pi/4 and 3 pi/4. That's why you see two cycles of the graph. However, we are going to focus on just one cycle between -pi/4 and +pi/4. The first step is to show your vertical asymptotes. We found the vertical asymptotes would be located at -pi/4 and +pi/4. That was done in step 1 of our graphing process. So at x equals -pi/4, we have a vertical dashed line indicating the location of the asymptotes. Asymptote on the left hand side, and on the right hand side we see another vertical dashed line passing through +pi/4. That's the first step in the graphing process. Show your vertical asymptotes. In the next step, we show the x-intercept, which is located exactly midway between the two vertical asymptotes. In this case, it's at the point of origin 0, 0. This is where the x-intercept of the tangent function graph lies. And in the third step, we will need to plot the points 1/4 way from the vertical asymptote on the left-hand side and 3/4 way, which would be a point somewhere here, from the left-hand side vertical asymptote. So let me mark those points. And in step 3 of our process, we found that the x values would be -pi/8 and +pi/8. Those would be the x values 1/4 way from the vertical asymptote on the left hand side, and 3/4 way it would be pi/8 for the x values. We know that the y values respectively would be -3 and +3. That was the value of a. So here we go. Between -2 and -4 would lie -3. Let's mark it somewhere here. So at -pi/8, we would have a y value which is -3. And then this is our x-intercept. And at +pi/8, the y value would be +3. Let's mark it here somewhere. And then finally, once we have all our points, we can just connect the points in the proper shape from the point of origin here for this graph, from the point of origin towards the asymptote on the right hand side. The graph rises first slowly and then steeply along the vertical asymptote on the positive side, and on the negative side the graph drops first slowly and then steeply along the vertical asymptote at -pi/4. All right.